Hi, now let's continue with Hopfield subnetworks. So we will contrast first Hopfield network with feedforward networks. Feedforward networks have connections that make up them to be acyclic graphs. So there are no cycles in the computational graph. And feedback networks, in contrast, are all other networks which are not feedforward ones. So networks that contain cycles in their computational graph. Now, Hopfield networks are fully connected feedback networks, so they do contain cycles in their graphs. They are also defined to have symmetric weights, and we apply to them the so-called associative or Hebbian learning rule. Here we've got a schematic of how a feedforward and a Hopfield network looks like. So as you see, the feedforward network has directionality in their edges, whereas the Hopfield network connects any two nodes in the network are connected with bidirectional edges. So information flows in both directions. With Hopfield networks, traditionally we have no separation between the hidden and visible variables, and the neurons update themselves in a recursive manner based on all other neurons. So these slides are, to make these slides, I used the excellent material in McKay's book, from McKay's book in chapter 42. So what is Hebbian learning? That helps us learn associative memories. Basically, the idea is inspired by biological neurons, and it is founded on the premise that positively correlated neurons should reinforce each other weights. So the weights that connect the jth neuron with the ith neuron should be proportional to the correlation that we have in the neuron response between these two nodes. Intuitively, you can think of it like that. If at time t, we've got a strong association between honey and being hungry, then we are reinforcing the associated neurons, so the honey neuron and the being hungry neuron, such that when we've got a similar activation, like a box of orange color, which looks a lot like our honeypot, then we would, by association, would also increase the neurons for hungriness. So this is how we create associative memories. So memories that associate part of the input with the rest of the input. It does require supervision, right? And you can also call this as pattern completion. So if the pattern is associating honey with hungriness, and I see something that looks like honey, then I can complete this pattern afterward. So a Hopfield network can be either binary or continuous. So for the binary Hopfield network, we've got a thresholding operation as to define the response of the neuron based on activation AI. Whereas the continuous Hopfield network uses a nonlinear activation function such as the hyperbolic tangent. There is a feedback connection, and this is a very important one, so very important detail to note. Between every two nodes, between every two variables, the information goes both ways. So X1 neuron influences X3, right, this green arrow, and in reverse, the X3 neuron influences X1. Now, the problem with this is who influences first. Like, we have to define an order, and we need to define it because these are recursive computations. So we have to be able to decide: are we going to first update our input to the neuron and then take the activation, then use the nonlinear function? Or we first apply the nonlinear function and then recompute the activation. So in general, we can have either synchronous updates, so we are updating the inputs to the neurons at the same time, and then we compute the nonlinearity, or we have asynchronous updates, so one neuron at a time, and then we recompute again and again, and the order then can either be fixed or it can be taken at random. Of course, all these choices can have a very severe impact on the behavior of our model. Now, Hopfield networks are very, how to put it, they're very well connected with memories, Hopfield memories. So that's actually what is quite nice about them. Our network will updates its states of neurons till they converge to a stable state. So we've got recurrent inference cycles, right? So the neurons reinforce each other again and again until basically they stop changing. So we don't have single propagation like with feed-forward networks. And here we can see two examples of what a Hopfield memory looks like. So if I have Moscow, of course by training properly on the training set, then I can complete the pattern and say that Moscow connects to Russia, or that in reverse Canada connects to Ottawa. And in a simple visual example, here are the memories that the Hopfield network has learned. So basically to recognize the letters D, J, C, and M. And then we can see that by disturbing a bit the state of our Hopfield network, it still sort of learns to go back to its stable solution and recover the original correct memory. Of course, the more complex the network becomes, your memories might not be always as recognizable as, like what you would expect. There might be something that is sort of doesn't look like a very clear pattern, but that is in general it can be okay, right? Like, because this can reflect generalization. Now, Hopfield networks in their original form, they're quite old models from the 80s. So by today's standards, all these achievements look outdated. However, I believe that associative learning is actually a very interesting idea, and as we will see, it has been explored recently with interesting results. So Hopfield networks basically can be shown to minimize the quadratic energy function like this. So f of theta is the sum of pixel combinations, pixel pairs, scaled by a weight parameter. And we also have a unary term, which is basically the prior over our pixel values. Now, what is interesting is that it can be shown that Hopfield networks are actually Lyapunov functions. And what are Lyapunov functions? They are functions that converge to fixed points. And why are we interested in that? We are interested in that because, sure, this is what Hopfield networks do, or, we defined even the Hebbian associative learning rule, but how can we be sure that the model can even converge? Maybe over time, instead of, the states converging to a single solution, maybe they start diverging. How can you know that? Well, you know that for Hopfield networks because they are Lyapunov functions, provided asynchronous updates and provided symmetric weights. And Lyapunov functions are functions that decrease over time under the dynamic evolution of the system. So as time passes, the function obtains smaller and smaller values, like the exponential, for instance. And they're also bounded from below, so they cannot decrease forever. They're going to decrease, but not surpassing a certain threshold. The learning algorithms of Hopfield networks is actually very simple, right? So you can write in a few lines, and I welcome you to go through it. First, you have to compute all activations, and here a sigmoid nonlinearity is used, not a hyperbolic tangent, but as we saw, this is not, it's basically similar to hyperbolic tangents. Then we compute the gradients and we make them symmetric such that we obtain a Lyapunov function definition for a Hopfield network, and then we update our weights, as simple as that. We can also define continuous time continuous Hopfield networks, which basically means that instead of having state variables, so instead of having discrete time steps, now our activations and our responses are continuous functions of time. So our response is the sum of the other neuron values at that time point, and these are computed instantaneously. So there is no discrete time step. Whenever there is an update, a new type of activation, a new type of response is computed. And then in that case, the neuron response is actually governed by a differential equation here, which it's pretty easy to show that it corresponds to the exponential of the minus of the input. So this means that if we consider, for instance, that we have a steady activation in a neuron, then the neuron response will gradually go to a stable state. Hopfield networks are, as we saw, recurrent in the sense that they are updating their neurons over time, and the neurons reinforce each other. One can also use them for optimization, so you can optimize functions under constraints, and basically the stable states are the solution of your network, and in that case the weights of your Hopfield network have to be optimal such that they don't only yield valid but also optimal solutions, right? So here, if we have the traveling salesman problem, it basically figures out how the salesman has to go through different cities so to discover the optimal solutions under the constraints that we have regarding visitations. And very recently, there has been this quite nice work that I think it might be worth checking it out from Ramsauer and others, and I think also Sepp Hochreiter, the author of LSTMs. So Hopfield networks is all what you need, and they show that they can, how you can retrieve interesting, how you can complete interesting patterns from stored memories, and they show that basically there, if you have an update rule that sort of resembles the attention mechanism in your transformer networks, this can actually make a difference. Thank you.